Guys, in this video, we will discuss about the Hessian matrix. So first of all, there is a question that why we introduce that new term Hessian matrix. Actually, finding the maxima and minima of a multivariable function is quite good or is better if we use the Hessian matrix. And by using the finding the maxima and minima of a multivariate function is also, we can say, that the optimization technique. So first of all, we have to know that what is now the Hessian matrix. Actually, the Hessian matrix, I'll just show you now. The Hessian matrix is the Hessian matrix of a function f of x is the matrix of second order partial derivative of f of capital X, where capital X is equal to x1 x2 dot dot xn transpose, and the Hessian matrix is defined by this term, that is J is equal to the matrix of del 2f del x1 to del 2f del x1 del x2 dot dot del 2f del x1 del xn, del 2f del x2 del x1 del 2f del x2 to del 2f del x2 del xn, and del 2f del xn del x1 del 2f del xn del x2 dot del 2f del xn 2. And we know that to find the maxima and minima of a multivariable function, if that contains n independent variables, then first we have to find the del f del x1 is equal to 0, del f del x2 is equal to 0, del f del x and dot del f del xn is equal to 0. And after solving this n simultaneous equation, we will get the points, and that points, and we will solve. Suppose we solve and we get x1 x2 dot dot xn, these points, and these points are always known as stationary points. And now we have to check at these stationary points what are the nature of the Hessian matrix. And at these stationary points, if we can say that a function that the Hessian matrix has a minimum value if the Hessian matrix is positive definite. This will give maximum value when it is negative definite, and there is no maxima and no minima when the Hessian matrix is indefinite. So now there is some new term we introduce here, that is the positive definite matrix, negative definite matrix, and the indefinite matrix. So now there is a question that how can we find, or how can we check that a matrix is positive definite, a matrix is negative definite, and when it was indefinite. So first of all, here we have to construct a matrix of order n cross n. Suppose here we will construct here a matrix Aij n cross n, and this is a square matrix, and this will give this representation. And then we have to find all the minors. That is, first one, this is the minors a1, that is a11. Next, the second order principal minor, that is a11, a12, a21, a22, and this is defined by a2. And at last, the total n cross n matrix gives the principal or the principal minor of the matrix A, that is defined by an. So now the question is that how can we say that the matrix is positive definite, negative definite, and indefinite? So now I will just conclude. I just look after this matter. So now we can say a matrix is positive definite if the leading principal minors are positive. That means if all the values of this matrix are greater, of the value of all the determinants are greater than 0, then we can say that is positive definite. And negative definite if the sign of ai is -1 whole to the power I. That means a1 is less than 0, a2 is greater than 0, and a3 is less than 0, and so on. Positive semi-definite if all the principal minors are greater or equal to 0, and negative semi-definite if all the principal minors are alternately less equal to 0 and greater equal to 0. That means here we can say that is like a1 is less equal to 0, a2 is greater equal to 0, and so on. And otherwise it will be say indefinite otherwise. So now and here one thing remind that the order of the Hessian matrix is always equal to the number of independent variables in the given function. So now I will just show you 1 and 2 problems regarding that how to find the maxima and minima by using the Hessian matrix. So here I consider one problem, that is f of x1 x2 is equal to x1 cube plus x2 cube plus 2x1 square plus 4x2 square plus 6. So first, this is the necessary condition, that is first you have to find the del f del x1 is, and see here that there are two variables x1 and x2. So the Hessian matrix is of the is a square matrix of order 2. So here we will find that first del f del x1 and del f del x2 is equal to 0, and if we find del f del x1 is equal to 0, we will get 3x1 square plus 4x1 is equal to 0, and if we simplify we will get x1 is equal to 0 or x1 is equal to minus 4 by 3, and if del f del x2 is equal to 0, we will get 3x2 square plus 8x2 0, and from here we will get x2 is equal to 0 or x2 is equal to minus 8 by 3. So now the stationary points are here, the origin 0 0, minus 4 3 comma 0, 0 comma minus 8 by 3, and minus 4 by 3 comma minus 8 by 3. And since there are total number of variables 2 independent variables, so the Hessian matrix is of the form J is equal to del 2f del x1 2, del 2f del x1 del x2, del 2f del x2 del x1, and del 2f del x2 2. And from here we can find the del 2f del x1 2, that is 6x1 plus 4, and del 2f del x2 is 6x2 plus 8, and see here that from here we can easily say that del 2f del x1 del x2 and del 2f del x2 del x1 both are 0. So now here we have to find the principal minors here, that is now the first principal minors we define it by J1, that is 6x1 plus 4, and J2 is the determinant of this second order matrix, that is 6x1 plus 4 into 6x2 plus 8. And now we have to find the nature of the J1 and J2 on these 4 stationary points. So now here if I show you that at the point 0 0, you just see here at the point 0 0, the value of J1 is 4 and the value of J2, that is 32, both are greater than 0, so we can say that J is positive definite. So 0 0 is a relative minimum, and at the point 0 the value of the function is 6. So now if we go to the next one, that is at 0 comma minus 8 by 3. So what we get here, that J1 is equal to 4 if we put, and similarly J2 is equal to again minus 32, which is less than 0. And see here that no property of the positive is, and this also satisfy the property of indefinite matrix. And since then if the Hessian matrix is indefinite, we can say that the point is a saddle point and there is no maxima and no minima. Now if we put here at the point minus 4 by 3 comma 0, so here we see that J1 is equal to minus 4, which is less than 0, and also J2 is minus 32, which is also less than 0. And from here you can say that minus 4, and this one satisfy the condition of indefinite matrix. So here we can say that minus 4 by 3 comma 0 is a saddle point, and so there is no maximum and no minimum. Another point last minus 4 by 3 comma minus 8 by 3, that is here we get J1 is equal to minus 4, which is less than 0, and J2 is equal to 32, which is greater than 0, and this will also satisfy the condition of negative definite. And we can say that at the point minus 4 by 3 comma minus 8 by 3, the function has a maximum, and at the point minus 4 by 3 comma minus 8 by 3, the value is 16.67. So I hope you understand the topic. So thank you.